misrepresented in the media. So I called it Hawking's black holes and the edge of physics, and hopefully all will become clear by the time we get to the end. Either that or I'll have confused everybody utterly. So this is Stephen, and he was born in 1942. He went to study physics somewhere else and then came to his senses and joined us over here in Cambridge in 1962 to do his PhD. But only a few years later, really, in this grand scheme of things, he was elected to be Lucasian Professor of Mathematics, 1979, and that was the post that Sir Isaac Newton had, so an extremely prestigious appointment for someone so young. And curiously, that was the same year that I came up to Cambridge as an undergraduate in 1979, and I nearly put an end to one or possibly two rather promising careers, because one night I nearly ran Stephen over whilst I was driving my motor vehicle through Cambridge. He came careering out in front of me on his chariot, so I was a very near miss. Of course, what made Stephen so famous was his book, The Brief History of Time, which I imagine most people have got, but often never really read or fully got to grips with. Well over 10 million copies sold, put it into the New York Times bestseller list. And I think they said it was the bestseller that was the least read. And the reason for that is I think there are one or two points within the book where people get lost and they get to a certain point, get stuck, and then put it aside. Now, I've listed the chapters there, and we're not going to go through all of them, but I'm going to use that as a bit of a framework to guide our talk about Stephen's work. The other thing that brought him to quite a lot of fame and attention more recently was the film The Theory of Everything, and box office sensation, the story of Stephen and his family. But it never really answered the question, what is this theory? And of course, the reason for that is that the title is a bit misleading. We don't have a theory of everything. And the media love to describe what Stephen was doing as the theory of everything, but really it was only one step along the way, perhaps a very important step, as we'll see. Now, because I give this talk to people who are not necessarily so familiar with astronomy and some of the terminology, we go back to Newton and gravity and the fact that planets and falling apples all obey the same rules. This was really the start of someone trying to put everything into one set of rules, one theory. A few things that are very straightforward and basic about gravity. If you jump up, it'll pull you back down again. But a question that you might not have asked yourself, what if the Earth was twice as massive? How high would you be able to jump? Have a think about that. Similarly, what if the Earth was squeezed to half its size? If we somehow magically crushed the Earth to half its size and you stood on the surface of the smaller sphere, what would the surface gravity then be? And perhaps you might think that the answer to those two questions is the same, but of course they're not. Then a very important concept for us in the context of this talk is the idea of escape velocity, and the idea that you can fire a large cannon up into space, and if you can get the cannonball to travel at 17,500 miles an hour, it will fall towards the center of the Earth in a path that's curving downwards, but it's the same rate of curvature as the shape of the Earth. So it goes into what we call an orbit. If you go a bit faster, 25,000 miles an hour, you'll have enough energy to escape Earth's gravity completely. So the idea is shown there in the diagram. Build your giant cannon on the North Pole, fire it slowly, the cannonball lands in the water. A bit further, it'll go over the horizon and still come to the ground. 17,500 miles an hour, it'll go right round and hit you in the back of the head. But if you manage to fire it at 25,000 miles an hour, you'll never see the cannonball again. It will escape. Now, very important to try and understand gravity properly. And often the media talk about there being zero gravity out in space. And clearly that's not true. The very first thing that Newton said was that gravity was affecting the moon and pulling it into orbit. So how can there be zero G in space? Now here's Stephen enjoying a ride in the zero G aircraft, the Vomit Comet. And what's happening is that the aircraft is taking a path down towards Earth that simulates the exact path that you would free fall under if you were just left to follow the path that gravity dictates. So everything around you seems to be doing the same thing, and it's as if gravity has disappeared, but of course it hasn't, and you only get 30 seconds or so before the plane has to pull up to avoid hitting the ground. Now, the other concept that we need to look at is the speed of light. And Galileo was one of the first people to realize that this was something you could perhaps go and try and measure. So he came up with an experiment. He sent his assistant to a distant hilltop with instructions to uncover his lamp that he was carrying when he saw Galileo's light. Now, when he uncovered his lamp, Galileo was going to try and time the delay before he saw his helper's light, which would be the round trip delay for the light to go from one side, front hilltop, to the other and back again. Now, of course, you're all going to realize immediately that this experiment won't work very well, because the human reaction time involved is going to vastly dominate any round trip delay time caused by the speed of light. And indeed, that's what Galileo found. And he concluded that light was extremely fast and at least 10 times faster than sound. So he was at least giving some sort of order of magnitude estimate. A little bit later, Ole Rømer tried the same experiment, only this time he enlisted the help of Jupiter rather than a glamorous assistant. And what he did was use the eclipses of the moons of Jupiter, in particular Io, moving into the shadow of Jupiter and then reappearing, simulating his assistant with a lamp, the lighting and covering of a lamp. And of course, now he's able to operate on a very much longer baseline. And the way that he was able to do the calculation was to time the difference in the appearance and disappearance of Io, depending on where the Earth was around its orbit. And in particular, if he timed it when it was at point G on my diagram here, it would be earlier than point F, because the light would have to travel that extra distance from G to F on the diagram. And he came out with a pretty good number, 220,000 kilometers per second, compared to what we now know the modern answer there, 299,792, or 300,000 as I tend to use. So anyway, with this, we now know that light travels at a finite speed. It's not infinitely fast. And that led John Michell, a clergyman astronomer. There were a lot of clergyman astronomers around about this sort of time in the 1700s and 1800s. He came out with the realization that you could calculate the escape velocity using Newton's different equations and work out how it would change depending on the mass of the object that you were trying to escape from. And he realized that a star 500 times bigger and equally dense to the sun would have an escape velocity from the surface greater than the speed of light. And therefore you wouldn't be able to see it. And he called these hypothetical objects dark stars, so the dark star hypothesis. And he realized that it could be quite scary because there could be a lot of these absolutely monstrous dark stars wandering around the cosmos, unseen. And, you know, we would not really want one of those to come wandering into the solar system because it would probably ruin your day. The next hero of this story that I'm going to just give a mention to is Karl Schwarzschild. He used Einstein's general relativity, which is Einstein's theory of gravity, to calculate the same effect, calculate for what would happen if you put enough mass in a small space, and it would result in gravity being so strong that the escape velocity would exceed the speed of light. And so it would cut off a region of the universe behind what is termed the event horizon of such an object. So you would never be able to see what was going on inside it. The same idea. And he calculated using Einstein's equations. And there's a very simple equation at the bottom there. R equals 2gm over c squared, where c is the speed of light. So r, the radius of the object, is proportional to the mass, just times a constant 2g over c squared. Very, very simple. Increase the mass, the radius gets bigger. Decrease the mass, gets smaller in direct proportion. Now, what's incredible about this particular feat is that he solved the really rather complicated equations of general relativity in 1915 while he was in the trenches in the German army on the Russian front. I guess there wasn't that much to do some of the time, and this was what passed the time for him. I think that's just amazing. So as I said, the Schwarzschild radius, which is given in that formula, cuts off an area of space-time, and we call it the event horizon because you cannot know what has gone on inside that new region of space. Nothing, no matter, no light, and no information is allowed to come out from inside. You just cannot see what's going on inside. If you cross inwards, you'll find out what's going on inside, but you'll never be able to come back and tell anybody. But this is not a game I would recommend. If you fell into a black hole, people often ask what would happen. And one of the effects is that the gravity gets stronger and stronger as you get closer and closer to the center of mass. And eventually your feet falling towards the black hole, like this astronaut is doing here, will feel a stronger pull than your head does. And the difference between them will be stronger than the material that you're made of. So you get torn apart, a process called spaghettification. I always put that in because the kids love it. The idea of being spaghettified on the way in. From outside, and this is where things start to get a little bit weird, the observer watching you fall into the event horizon will never see you cross it. Light coming out from inside, from the towards the event horizon, is climbing uphill away from the source of gravity and is redshifted to longer and longer wavelengths and lower and lower energies. It's losing energy as it's climbing out of the hill. But the other weird thing is that time is affected, and if you carried a large stopwatch with you, then the outside observer would see your clock start to tick more and more slowly. Essentially, the gaps between the ticks are getting longer in the same way that the peaks in the wavelength of light are getting further apart and arriving with a greater interval between them as the light is getting redshifted. So you would see the stopwatch get redder and redder and tick more and more slowly until it would fade and freeze in place on the event horizon. And you would essentially, there would be one last photon that would come from it just as it crossed into the event horizon and disappeared. But the person with the stopwatch falling in would not notice any of this. Everything would seem perfectly normal to them. This is pretty weird. And it leads people to start to question whether or not the whole idea of black holes are real or not. And so to just talk about black holes specifically for a moment, We believe that they're formed in a number of ways, and one of the most probable is to be the collapsed core of an exploding massive star. When a star greater than about 15 solar masses blows up, blowing the outside layers away, and the central core undergoes an implosion and crushes it right down. If it's not quite big enough to form a black hole for our purposes, then it'll form a neutron star. What happens is all the electrons and protons are crushed together to form neutrons, and then you end up with a ball of neutrons with the density of an atomic nucleus, and has a staggeringly high density figure to it. 1 billion kilograms per cubic meter, I think, is approximately the right number, 10 to the 18. And here is an example of one that was detected, the Crab pulsar. It's a spinning neutron star with a very strong magnetic field. And I don't know whether you can hear it, but I'm playing the sound, so I'll shut up for a moment. Can you hear that? It's probably rather faint. That's the sound of the clicks of the radio waves coming from the Crab pulsar, coming our way, being detected by radio telescopes.
Yeah, we can hear that, Paul.
Splendid. But if that core, that imploded core, exceeds around about 3 solar masses, then there is nothing, not even the strength of the neutron matter, can resist the crushing power of gravity. And so nothing can stop the collapse continuing, and the matter gets crushed down, possibly to a singularity right in the center, but that's hidden behind the event horizon of the black hole that is born as a result. So we can never see these singularities. One of the good examples of this was Cygnus X-1. This is an example of a binary star where the two components of both giant stars, the first and larger component has evolved right through the main sequence, burning hydrogen, through the red giant and later stages, and then collapsed through a supernova explosion and formed a black hole. And now its companion is catching up and has gone into the giant phase. And that expansion has allowed some of the material to be drawn away and spiraled down under gravity into an accretion disk that gets superheated, hot enough to give off X-rays as it's in its death spiral, falling down towards the black hole to be consumed by it. Now, in 1975, Stephen Hawking and Kip Thorne had a bet about this, and essentially Stephen bet against the existence of black holes as an insurance policy, and finally, eventually signed off that the bet was lost, and the evidence really became overwhelming. Cygnus X-1, the central object, the compact object, we can work out from the orbits, from Kepler's laws, that it has a mass of 14.8 solar masses, so it's way too heavy to be a neutron star, and it's only around 300 kilometers across. The reason we know it's that size is because it flickers in X-rays every 1 millisecond, and a millisecond, 1,000th of a second. Well, means that the distance that light can travel in a millisecond is just 300 kilometers. And so for any physical process to be able to operate at that speed can't be larger than the time that light would take to go from one side of it to the other. And the only way that you can compress 14.8 solar masses into 300 kilometers is for it to be a black hole, according to the theory. It's just a matter of plugging the numbers into that Schwarzschild formula. Also, we find black holes at the middle of galaxies. These tend to be much more massive, supermassive, million or billion solar mass monsters. And right at the center of our galaxy, the Milky Way here, there's an object that's giving off radiation in X-rays and radio waves and all sorts, called Sagittarius A star. Now there's a zoom in of the center of the galaxy there, showing that there's a region of hot gas and surrounding the area where Sagittarius A star appears to be. But we can zoom in a bit further on it and a bit further still and get an X-ray close-up of what looks to be that hot gas, million-degree temperature surrounding the black hole, giving off a lot of these X-rays. So probably spiraling into their last final consumption by the black hole in the middle. We can also plot the orbits of stars that are orbiting around Sagittarius A star. And here we see a number of the stars performing their orbits around where somebody has kindly put the red X in the middle there. The little red cross marks the center of mass of the orbits. And you don't see an object there at all. Now, if you look at the star that's doing the nice elliptical orbit, just reaching the top now, you can easily work out from the ellipse of that orbit how much mass there is in the middle. That star there takes 15.2 years to go round once, and that works out to just under 4 million solar masses of material right in the center there. I had my GCSE students do that calculation for me just the other day. Now, one of the other stars that's going even closer to it on the long, thin orbit, coming in from the top left and going back out to the top left, is making a very close approach to that center as well, closer than the planet Uranus orbits the sun. And again, the only way that you could fit 4 million solar masses inside a volume equivalent to the orbit of Uranus is for it to be a black hole. Now, black holes can be very messy eaters. When they're having their lunch on these accretion disks, these material that's spiraling in, quite a lot of it gets tangled up with the spin and the magnetic field of the black hole and is shot out along the polar axes as jets traveling at nearly the speed of light. And we see that in a number of places. In our own galaxy, we see regions above and below the plane of the galaxy called the Fermi bubbles, which are very hot in X-rays and gamma rays that we're detecting coming back. And this suggests that some time ago, perhaps around 6 million years ago, the black hole in the center of our galaxy was having a real feast and shooting enormous jets out above and below the galactic plane like that. And such an object would be called a quasar. We see them from right across the far distant corners of the universe. There's one with the big arrow pointing at it here that's 9 billion light years away, yet still shines brightly enough for us to detect. And as it says on the slide there, they were discovered in radio surveys to begin with, then optically, and the redshift in the optical showed just how far away they were. The light's been traveling for 2/3 of the age of the solar system before it landed in the camera that took this shot. I think that's a quite incredible statistic. And as I said, what they are is the feeding black holes in the middle of young galaxies when they were young and very, very active before they tend to settle down in middle age, a bit like our Milky Way has, which is probably no bad thing, because I don't think you would want to try living in a galaxy that had a very, very active black hole right in the center, pouring all this radiation out. Now, the other evidence that we've got for black holes comes from detecting the mergers of pairs of them, and this is through the emission of gravity waves. This is a simulation here, this animation, showing a large black hole and a smaller one orbiting each other and eventually merging and settling down. And you can see the disturbance in space-time that they're causing around them, making all of the stars in the background image there wobble. As I say, this is a simulation. I wish we had a real image like this, but telescopes are not good enough yet. But the telescope that was used to detect this for the first time was LIGO, the Laser Interferometer Gravity Wave Observatory. And there are two of them in the United States and more now operating elsewhere in the world. The idea is you have these two 4-kilometer long arms, and you take a laser beam and split it, sending part down each arm. Actually, it goes up and down the arms many times and is then recombined in the laboratory at the center point there. And any shift in the apparent length of the flight path of the laser beam caused by a distortion in space-time passing through the observatory will result in a shift in the agreement of the re-arrival time of the laser pulses. And they indeed, after they'd done the first run of LIGO and weren't able to detect anything except the odd passing train, they upgraded the instrumentation and then turned it back on and immediately were successful in discovering the arrival of a signal from a pair of merging black holes. So there's the simulation again, but the data on the left is the real data from both the Hanford and the Livingston LIGO laboratories in the top and middle rows there, compared with what you would predict for a pair of merging black holes. And then we've overlaid them. You had to shift the time a little bit because the gravity waves travel at the speed of light. And so they arrived at the two different observatories at slightly different times due to the angle they were coming in from. Now, that wiggly signal with the waves getting shorter and louder until the final merger can be converted into a sound, and I've got that playing for you, so I'll just stop talking for a moment and you'll see if you can hear it. There it was. What happens is that the sound gets starts from a very low frequency below the level that the human ear can cope with, and then as the two get closer and closer together, the pitch rises to the point where our ears can pick it up. And of course, fairly recently, we've had the Event Horizon Telescope, which was a collection of radio telescopes across the whole of the Earth, giving us the most high-resolution image ever of the black hole accretion disk around the supermassive black hole in the elliptical giant galaxy Messier 87. So M87 is shown on the left there, and you can just see the jet coming out of it, of matter coming away from the black hole. And the orange image on the right with the black hole in the middle shows the accretion disk around that black hole, which is probably around 1 billion solar masses. It's a absolute monster. So I think there's a lot of evidence that these things really do exist. So let's get back to Stephen and his masterpiece. In 1974, he realized something about black holes, which is that they appear to violate the laws of thermodynamics, the laws of heat transfer, and the laws that govern whether heat flows from a hot object to a cold object are very well known, but there was a problem with that in that if you had energy flowing into a black hole, well, then you had to define what the temperature of the black hole was. And given that it didn't emit any radiation at all, that was a bit of a problem. And Stephen realized something about this and wrote a paper on the subject that shocked the scientific world. And the reason it was such a shock was that it was the first to combine in one mathematical framework quantum mechanics, the science of how very small particles behave, general relativity, Einstein's theory of gravity on the large scale, and thermodynamics, all into one calculation that didn't blow up in his face. Previous attempts, and indeed a lot of subsequent attempts using these together, result in giant infinities that you can't get rid of appearing in your calculations. And he came out with the resulting statement, black holes ain't so black, which is the title of chapter 7. So we've kind of skipped forward past black holes in chapter 6 there and onto chapter 7, the idea that black holes ain't so black. So what is he actually saying? Well, to understand it, first we need a couple of the earlier pieces, and in particular we need to look at the quantum mechanical idea of the uncertainty principle. This is a picture of Werner Heisenberg, who was the first to come up with the idea and really has his name associated with it. And the principle is that you can never know everything about a quantum system. More specifically, there are pairs of quantities which the uncertainty in knowledge about one is related to the uncertainty of the other. It's a complicated way of saying the better you know one quantity, the less well you can possibly know the other. And this is not a question about how good your equipment is or how careful you are at measuring it. It's a fundamental limit on the information that you are able to extract. A little bit of maths for it. What it says is that if you take two quantities, delta x, which is the uncertainty in the position of a particle, and delta p, the uncertainty in its momentum, in other words, in how fast it's moving times its mass. If you multiply those two together, you always get a result that's bigger than a constant, and the constant is Planck's constant h divided by 4 pi. And so for a particle like an electron, this means that the better you pin down its position, delta x, the less well you can possibly know its speed. The momentum uncertainty naturally is forced to increase. And so no sooner have you tracked your electron to be in one particular spot that it's moving off at some very large undetermined speed to be somewhere else shortly afterwards. So that measurement's not actually terribly helpful. But you can write this another way. Instead of delta x times delta p, you can swap to energy and time coordinates. So you can say that the uncertainty in the energy of your system multiplied by the window of time that you're concerned with is also always greater than h over 4 pi, or h bar as it's written there. And this means two very, very important critical implications. The first one is that for short periods of time, energy can be very uncertain. And this allows quantum systems to violate the conservation of energy, provided they pay back the energy quickly enough. It's as if they're borrowing energy from the cosmic bank and giving it back so fast that they're not being charged interest on it, and the great cosmic accountant is not noticing that they had an overdraft. But it also means that empty space can never have precisely zero energy. If the energy of empty space was nothing, if you took a box and you sucked all of the molecules and atoms out of it and somehow arranged that there was no energy at all, no photons, nothing in the box, then you would think that the energy of the space in the box would be zero. But this cannot be, because if it was zero, then there would be no uncertainty about it. And that is going to break this uncertainty principle. It's just not allowed. Now, before I go on, I also have to talk a little bit about antimatter and the idea that we and all the matter around us are made of ordinary matter, where we have positively charged protons in the nucleus of our atoms and negatively charged electrons going around them. But you can get the opposite case of antimatter, where you have antiprotons with a negative charge and anti-electrons going around them, the E plus there on the little picture at the top. And we've created antimatter in the laboratory. You can build a few hydrogen atoms of it. It's the most expensive material that has ever been created at several $1 trillion per microgram. But you can produce this stuff in particle accelerators and elsewhere. But the thing about it is that if ordinary matter and antimatter get together, then they cancel each other out and you get a blast of energy released. And of course, that's because the energy E is equal to the m, the mass that you have destroyed, times the speed of light squared. E equals mc squared, the most famous equation in the world. But E equals mc squared works both ways round. If you take energy, you can make particles from it. And this is the sort of thing that particle physicists do in accelerators. And it's also what happens in cosmic rays coming crashing into the atmosphere. We get showers of electrons and anti-electrons called positrons coming down into the atmosphere as a result of gamma rays colliding high up in the atmosphere. So if we go back to the uncertainty principle, the reason that empty space is not zero energy turns out to be because energy is constantly being borrowed from space-time, and a pair of particle and antiparticles are briefly popping into existence before recombining and annihilating and giving the energy back within that time limit set by the uncertainty principle, so that the cosmic accountant is kept happy. But it means that on average, there is a net positive amount of energy in the vacuum, in the empty space. Its average energy is always above zero, just because of this constant churning of short-lived pairs of particles and antiparticles. And if this sounds crazy, well, I wouldn't be upset if you thought it was, but it's been measured in the laboratory to be true. Henrik Casimir predicted an effect in 1948 of holding two metal plates very close together in a vacuum chamber. And the result of quantum mechanics is that the gap between the two plates excludes certain quantum fluctuations from being possible because their wavelengths won't fit in the gap. And the result of that is that there's more quantum fluctuations outside the plates than in between them. And you get a pressure pushing the plates together. And you can actually measure this. If you get your plates 10 nanometers apart, then you can get a pressure of about 1 atmosphere. This is no small effect, and turns out to be really rather important in all sorts of things. What's all this got to do with black holes, though? This is where Stephen pulled all of these various different bits of physics that I've been talking about together, and he came up with a realization. If you had a particle-antiparticle pair created far away from a black hole, they would appear and then re-annihilate and give the energy back. Everybody's happy. But if the same thing happened near the event horizon of a black hole, as shown down to the bottom here, one of the particles might accidentally fall into the black hole, and then it's not able to climb back out again. It's lost forever. So now its partner has nobody to annihilate with and goes on to become a real particle. But wait a minute, what's happened? Somehow we've created something out of nothing here. Well, what Stephen showed was that as the particle falls into the black hole, the blue particle drops in below the event horizon and is going down the gravity slope. This is releasing energy from gravity, and that energy is used to repay the debt, the energy debt to the great cosmic accountant, and allow the escaping partner particle to become part of the real universe outside. So the result is that the event horizon of a black hole appears to have particles radiating out away from it. They're appearing to come from the edge of the black hole. They're not coming from inside it. The partner particles are falling in and disappearing, and the ones that we see are the ones that have always been outside and get away because they've had their debt paid by the partner that fell in. And the result is that black holes ain't so black. They appear to give off this radiation, which we now call Hawking radiation in Stephen's honor. And Hawking calculated in his paper exactly how much of this radiation there would be across the event horizon of black holes of different sizes. And what that amounts to is assigning them a temperature, an amount of radiation per second that's coming away from an object is that basically the temperature. And that solved the thermodynamic problem of the fact that he didn't know what temperature to assign to things in the first place. But it has another startling implication, all of this. Energy to repay the cosmic accountant for the Hawking radiation that is coming away from the event horizon has to come from somewhere, and it comes from the gravity of the black hole. Now, you might consider that the black hole really is just a ball of rolled up gravity, of gravitational potential energy. And because E equals mc squared, energy and mass being the same thing, as the black hole loses energy by giving it up to emit the Hawking radiation, it loses mass. And so gradually, the black holes are going to evaporate completely as they lose all of their mass. Now you can draw a graph like this, which is helpful in understanding something about what happens for different sizes of black holes. What this is saying is that a large black hole over to the right of the diagram has a very gentle slope to its gravity, and a very small black hole has a very steep slope to its gravity, much nearer the left-hand side. So if you have a very large black hole, a particle falling in to release its partner to the outside world has to move quite a long way in the space direction in order for the change in the gravitational potential energy to be enough to pay for its mate that's outside. It has to go a long way in the x direction because the slope is very gentle. Whereas small black holes, the slope is very steep, and so you don't have to move very far at all. And of course, you're up against a time limit. You have to pay for the energy within that cosmic uncertainty principle time limit in order for this to be allowed. And so large black holes find it quite difficult to give off Hawking radiation. And that's because it takes a long time to move a long way to gain enough energy to pay for the creation of the partner particle. So it's unlikely, and they have a low Hawking temperature. But tiny black holes can do this very much more easily, and so they have a very high Hawking temperature and they evaporate really fast. So you can see this is going to be a runaway process. As the black hole gets smaller, its Hawking radiation is going to increase, and it's going to therefore lose mass more quickly and evaporate ever faster. Now you can calculate the Hawking temperature for a solar mass black hole, and the figure comes out to be 1/10 millionth of a degree above absolute zero. So they're pretty cold. In fact, so cold, it's much colder than the microwave background radiation left over from the Big Bang. That's 2.7 degrees Kelvin. And so actually there are more cosmic microwaves falling in, feeding a solar mass black hole, than there ever is Hawking radiation coming out. So it's not going to shrink, it's going to grow, feeding on those cosmic microwaves. So it's not going to evaporate away. Well, what if we looked at a smaller black hole? about we take the moon, and don't try this at home, turn it into a black hole. You'd have to crush it to 10 micrometers to do so, to get the density high enough for that event horizon to form. But if you, the Hawking temperature of such an object would be 2.7 degrees Kelvin. And so it would sit there in balance with the Hawking radiation coming out at the same rate that cosmic microwaves were falling in. But if you instead took Mount Everest and made a really tiny black hole, then it would have a Hawking temperature that would be in the tens of thousands of degrees towards the end of its life. And such objects would slowly lose mass and get hotter and hotter and hotter. And if created in the very early days of the Big Bang, then perhaps we would see their final death throes from across the cosmos, because they would go through this last runaway phase where the temperature would rise exponentially. And in the last second, they would have the power output equivalent to 10,000 stars and look somewhat like a supernova. So if these primordial black holes were created, we should see them evaporating and looking a bit like a supernova. But of course, the spectrum of the light would be different, so we would be able to tell. But we haven't spotted one yet. Also, I don't know whether you remember that there was the question of whether or not we should turn on the Large Hadron Collider, because there was the chance that this might make a microscopic black hole, which would then grow by feeding on the apparatus itself and then swallowing the whole of the Earth. Well, according to Hawking, microscopic black holes evaporate so fast they would never reach the edge of the container. So we assumed it was safe and we turned it on, and we're all still here. Except for the fact we really knew it wasn't going to happen, because cosmic rays in the upper atmosphere would have done this experiment for us. They're very good at simulating particle accelerators, so we knew it was safe. But we're running a little bit behind schedule on this talk, so I'll skip this, except to say that we know that gravity also bends space and bends time. And we have to use this when we're allowed to drive our cars around again. We'll be using sat-nav, and the sat-nav depends on us calculating for the effects of general relativity to allow for this bending of space and time around even an object as massive as the Earth. And if we didn't, then we'd be 1,000 meters off in locating where we were on the surface of the Earth if we just used Newton's laws.
Oh, we're not restricted by time, so if you want to go.
Okay, that's excellent, Dave.
Okay.
I shall continue at a sensible pace. So the idea of that bending means that you could kind of draw a black hole as a really dense object where gravity's disappearing down a funnel shape like this, perhaps down to an infinitely deep point, a singularity. It's a popular way of looking at them. It's so deep that you can't climb out. But you could take one black hole, chop the singularity off somehow, bring another one up, connect the two together, and this is what you would have as a wormhole, connecting two regions of space-time together through that narrow neck, making effectively a tunnel. It'd be very useful if you could do this, because you could create shortcuts across the universe, save all that pesky traveling from the Earth round to a distant star. You could pop through your handy pocket wormhole and come out somewhere else in very little time indeed. And Einstein's theories do indeed predict that this is all possible. However, the mathsy bit on the left and the coloured diagram shows a wormhole being held open by a donut shape of red stuff around it. The only problem is that to make a wormhole stay open, you need that red donut around its throat. And that red donut has to have negative energy. In other words, negative mass. It has to weigh less than nothing in order to keep the wormhole from collapsing. And we've never seen anything that has less than no energy or less than no mass at all. But the maths says it's all good. And it was all predicted by Einstein and Rosen. They're called Einstein-Rosen bridges. That's another name for a wormhole. Now, when we were looking at the Event Horizon Telescope, which imaged that black hole, if we'd seen something more like this, then we would have known that it was a wormhole. And it's worth going and looking at various different parts of deep space to see if we can see nature's best telescope. Because if wormholes somehow did get created, you would be able to look through them and see the image of a very distant piece of the cosmos through them. Now, the only one we've seen so far was the black hole in the center of M87, and it was indeed black in the middle, not showing us a tunnel through to another part of the universe. So better luck next time. But by the same token, all of this mathematical modeling of bending of space-time means that if you could kind of manipulate space to make half a wormhole, then you could fold space like this, crushing it in front of your spacecraft and expanding it behind, and that would propel you forwards in a little puddle of flat space. So you wouldn't feel you were moving, but you would see the universe whizzing past you, Star Trek fashion, and indeed this would be a warp drive, and there is no reason why you could not build a warp drive, except for the fact that in order to create this distortion in space-time of the right shape, you need some more of that negative matter to create region 3 there at the front. But if you can create a wormhole, you can create a time machine, and you can travel not only to a different where in the universe, but to a different when by falling through one of these. And that opens up all sorts of amazing possibilities. But again, the maths doesn't say it's impossible, except for the fact that it says that no wormhole can take you back to a point in the past earlier than the time at which it was created. So perhaps the fact we don't see thousands of time tourists wandering the streets means that no one has created one yet. But the moment we do, suddenly they're all going to start to come to visit that event, I think. And this neatly segues me into the last bit of Stephen's book, which is chapter 9 here, The Arrow of Time. I've skipped over the origin and fate of the universe. I'll cover that in a separate talk, but we're going to end really with the mind-bending aspects to this, particularly around this idea of the arrow of time. We live 13.8 billion years from the Big Bang. We're in the Big Bang's future. And there's a curiosity, which is if we calculate the radius, the Schwarzschild radius of a black hole, that would contain all the matter, including the dark matter, subject of another talk, that we see around us, then we find it comes out to 13.8 billion light years. In other words, it's as if nature is telling us that we live in a black hole of the radius of 13.8 billion light years. The calculation's a little bit more complicated than that, and the numbers are a little bit different, but you get the idea. Now, if you were to travel into a black hole, obviously you'd never be able to come back and tell anybody about it. But what you would find is that space-time becomes very weird. It becomes so curled up at the singularity that all possible future, inside the black hole, it becomes so curled up that all possible future paths in space lead you to the singularity in the center. And at that central point, the curvature of space-time becomes infinite. What this means is that time stops at the singularity, and there is no after. There is no future time, and there is no beyond the singularity. The media love to talk about the idea that you would pop out into another universe if you traveled through here, but it's not really something that makes physical sense of traveling through in the same coordinates of space and time that we understand and popping out somewhere else. So really, this singularity is the end point of physics. But you can say the same thing about the singularity at the Big Bang, where everything came from. Time began at the Big Bang. There was no before or beyond, and it's the beginning of physics. And in the universe we see today, all possible past paths lead back to the singularity. Now, can you see the symmetry here, that the singularities inside a black hole have all future paths leading to them, and the singularity at the beginning of time at the Big Bang has all past paths leading from it. No matter which direction you look in the universe, you're looking back towards the Big Bang singularity. And what this means is that the world lines, the paths of all particles through space-time, begin at the Big Bang singularity, and many of them end up at the singularities inside black holes. It's as if time flows from one singularity to another, begins at one and ends at the other. And if you swap the direction of time over, that arrow of time, reverse it, then black holes suddenly look like sources, and the Big Bang looks like a sink. So the Big Bang looks like a black hole, and the black holes look like mini Big Bangs. So is it possible that one interpretation of this is that inside of a black hole, time appears to be reversed, and you would perhaps perceive that the singularity that we think is in your future is actually in your past, and it would look rather like that was the Big Bang in your mini universe that you now found yourself. And the thermodynamics aspect of this is that the arrow of time always points from order to chaos. It always points towards increasing entropy. And the universe, the Big Bang, started in a highly ordered state. There was everything in one spot, and is leading onwards to a multitude of chaos and chaotically organized black hole sinks. So the past world lines of all particles lead back to this, but flow forward to a chaotic future. Is that the reason that the arrow of time points that way, and that we can only remember the past and we don't remember the future? Is it all just a matter of the perspective that we put on things? And with that, I shall stop. And I hope that's given you things to think about, and probably made you think about time and black holes in ways that you perhaps have not thought about them before. Thank you very much for listening. I hope you've enjoyed that. I'll now stop sharing my screen and hand over back to our lovely host, Mr. Dave.
Hello, right. Thank you very much, Paul. That was absolutely brilliant. Really, really enlightening. And I love this concept about a cosmic accountant. Really love that. Okay, has anybody got any questions they'd like to ask?
Yeah, Paul.
Hi there.
If you had two black holes that formed in identical conditions, but one condensed out of matter, one condensed out of antimatter, would they be the same? And if they merged, would they annihilate, or would they just form a bigger black hole?
God, that's a really hard question, isn't it? I think that we believe that the nature of the matter or antimatter that created the black hole in the first place becomes lost. and that both of them essentially get crushed out of existence and converted into pure energy. And then there is no anti-energy. Yeah, E equals mc squared, regardless of whether M was matter or antimatter, and that you therefore can't tell the difference. But the whole piece of this that I skipped over is the idea that Stephen was still grappling with towards the end of his life, which is called the information paradox. And this is, if I have a pair of odd socks, a red one and a green one, I throw the green one into a black hole. Does the universe remember the greenness of my odd sock? And does the Hawking radiation somehow, if the black hole evaporates, does the Hawking radiation just carry randomness, or does it carry the history somehow of my green sock? And we never did get to the bottom of that one. No one knows. And actually that's at the heart of your question as to whether matter and antimatter would retain their identity.
Thank you.
Okay, any other questions from anybody?
Can I ask one, Dave?
Yeah, of course you can, Pat.
It sort of follows on from that one. It's about the particles breaking up and falling into the black hole. If a positive particle falls in and an anti-particle doesn't fall in, does it become positive, or does it get annihilated? What happens to if you see what I mean?
Yes, I do. Actually, it turns out not to matter whether the thing that falls in is positive or negative, or matter or antimatter, because its identity gets destroyed. It's the same point as the previous question. Its partner survives, and we would imagine that the radiation coming away from the event horizon, the Hawking radiation, should be a mixture of all possible types of particles, including matter and antimatter. Now, of course, because our universe has a lot of matter in it and not much antimatter, any antimatter coming away in Hawking radiation isn't going to get very far before it will bump into an ordinary counterpart particle and annihilate, and then you'll just see a flash of radiation coming away. But your question's absolutely right. Both types can fall in and the other particle survives. Both types have positive mass, even if they're matter and antimatter. Yeah, and so they have positive energy, and the one that falls in gains energy to pay for the surviving positive energy particle that gets away. That's how you have to think about it.
Thanks very much.
Can I ask a question?
Gavin, yeah, go ahead.
Yeah, you showed a simulation of two black holes merging together, but well, when you think of stars merging together, material from one star would fall into another star, and eventually the two would merge. If a black hole, if nothing can get out of a black hole, how can the two black holes merge together?
Yeah, so what happens is that as they're orbiting around each other, the two black holes, they're both distorting space-time with their gravity. And the result is that waves of gravitational energy are coming out away from them, rather like water waves on a pond when you throw a stone in. And they carry away energy from the system. And the result of that is that the two black holes spiral in towards each other because they're losing energy by giving out these gravity waves. It's the gravity waves that we detected that told us what had happened. And in fact, what I forgot to say in the talk was, in the case of the LIGO detection, the two black holes were, roughly speaking, I think 20 and 30 solar masses each. And when they merged, they formed one black hole which weighed in at 45 solar masses, and the other 5 solar masses was converted into the energy of the gravity waves that went in every direction across space, and we detected a little tiny bit of here on Earth.
No, sorry, another question. When you showed the simulation, everything seemed to happen quite quickly. The two black holes seem to merge quite quickly, but in reality, how long would that take?
The event lasted of the order of tens of seconds.
Right.
In the bit that we detected. Obviously, they'd been spiraling each other for astronomical periods of time since their formation, but it's an ever accelerating process. The closer they get to each other, the harder they push out energy in gravity waves, and so they spiral in ever quicker, which is why that last little bit, you hear the tone of the frequency go chirping upwards. It goes rip at the end, and that's because they're orbiting each other maybe once a second when you first detect it, and then it's 10 times a second, and then it's 100, and then it's finally 300 times a second that they're orbiting each other before they bump and then merge.
Okay. Okay, any more questions? No? Okay, if that's the case. Paul, thank you very much for absolutely stimulating and interesting talk. Now, all of us know a little bit more now about Stephen Hawking's theories and the black holes as well. So, brilliant. Okay, so without further ado, thank you very much, everybody, for coming in tonight. Thanks, Paul, for giving an absolutely outstanding talk. And I'll see you all in a couple of days' time. Keep safe and keep well, folks.
Thank you.
Thank you.
Thank you.
David.
Bye. Thank
Thanks,
you.
everybody. Thanks, Paul. Great talk.
Thank you. Very good talk. Thank you.